So let's get started. So today we're going to talk about privacy. And in particular, we're going to get to differential privacy. So that's why so let's get started. So today we're going to parentheses. Okay. So we're going to get to this lecture will be somewhat historical. We're going to kind of talk about kind of the history of releasing of data in the era of data science and how privacy became a concern in that time, what the community tried to do about it, and there are a bunch of different proposals and kind of some touch points of where this kind of worked and where it didn't work. And we'll eventually get to differential privacy, which is kind of if you ask someone what is the most foundationally correct way to do privacy, this is what they will say. And I'll say kind of where it works and when, and maybe some of the reasons it hasn't been as adopted as widely as we might want it to be. So before we get started, let's look at this schedule. So we split homework 6 up into 2 parts, and the first part on the noise, outliers and anomaly detection is due on Wednesday. It should be, if it seems hard, you're probably not doing it right. Okay, so it's meant to be pretty simple. It's half an assignment. The data set is like 100 data points. Should be pretty easy to see what's going on, but just enough to get you to kind of work through and do some of the basic sort of calculations you would expect to in this space. If you have questions about it, you can ask. It's been posted, right? The homework is here. Hopefully it's pretty straightforward, although you work through some of the calculations we did in the anomaly detection part, and I wrote them up in the complicated form, but what you actually should calculate should be something much simpler if you simplify these expressions. So give you a chance to work through doing that, and kind of this sort of simplification shows up all the time in this space. So it's good to get a little practice doing it. Okay, the other things that are coming up, the final report is due already in under 2 weeks. Okay, so hopefully you're kind of been working on that a bit since your intermediate report. This is the day before Thanksgiving, so you can do it and then enjoy your Thanksgiving break doing all the projects for your other courses. Remember that'll be 4 pages per person in the group. So it can be less than that. That's fine, but don't don't go over that. That should include the graphics and figures, right? Those should not go in the appendix. One thing I found about scientific writing is that forcing an upper limit on it actually often significantly improves the writing. Not all the time, but in many cases. So I think hopefully this constraint is useful and allow you to focus on the important things. Okay, also Wednesday in class, we'll be doing an in-class activity. I didn't put this on the original syllabus for grading, and I want to make it a graded thing. So what we'll do is we'll count it as an extra assignment, but if you turn it in, you can drop 2 assignments. So if you turn it in, you'll probably get all the points on it, and that'll allow you to drop another one, assuming you finish all the assignments. There'll be a kind of in-class activity. One of the reasons is the final report, I'll want you to do supposed to be doing an assessment of the like an ethical evaluation of your project. And so I kind of wanted you to be thinking about this at the very end, kind of go through the exercise of doing it and then think about these sort of issues. And so what we do in class will give you kind of some practice for doing that on a kind of toy example that you get to work through. So there's not a right and a wrong. You won't get in trouble if you realize, oh, maybe this was kind of like was dubious in some way. I want you to kind of think through this kind of exercise at this stage. This is a learning experience. We're not not deploying these things in the world. And then so that'll be in class. If you cannot make it to class, I want to be flexible and allow you to join on Zoom. So I sent out a Zoom link as well. And so you can join on Zoom and I'll do breakout rooms, but it'll be a little bit better to do in the classroom. If you have an HDMI cable, it might be useful to use the big screens on Wednesday. So if you would bring one in, I'll have you break up into groups, and each group can use one of the screens. So that if you have one of those, that'll be good to bring on Wednesday. Great. So okay, that's where we are in the schedule. Okay, privacy. So far we've mostly been talking about. So we have a data set X, right? And we could think of this as this like matrix often, where we have these attributes and these so data points, right? So I can have each of these rows is going to be a data point. Each of the columns is going to be like an attribute, right? And so the main thing I want you to take away from kind of the privacy and then kind of going into kind of the ethics kind of lecture, and it can go to things beyond this. But if there's a data point, so like I want you to think through what if this was so what if this was you, right? So what if this data point, we're analyzing these data points, we're trying to make some categories or kind of embed stuff similar to other data points. What if this data point was you? Would you like the consequences of being kind of grouped together or used to make an inference on things with the data representing yourself, right? And so I want you to think about the ethics of this as being from the perspective of like empathy, where if that data point was you, but actually when you're doing the analysis, it may not be your actual data point, it could be someone else's data being represented here. Would you be okay if that was your data? All right, so I think if you approach it from this perspective, you're going to have a pretty healthy view of it, and you're going to make some healthy decisions. I don't think it's my place to tell you what decisions to make with it, but to give you some guidance. I think this is a pretty good principle. Okay, we'll be talking about in this lecture, the Wednesday will be a bit different, but this lecture will be thinking about, well, what if attributes of your data got leaked out into the public or to various people who may want access to some of your data when you thought it was not available to them, right? So that's kind of the issue with privacy. And so the privacy in data. So the question is who gets access to it and to what? Okay, so when there's data available in these, and we'll go through a number of examples, there'll be different aspects of the data. Some of it is you'll probably be like, okay, that's fine if everyone knows about this part. But there are other parts you might think are you'd be a little bit more uneasy if like people were aware of this. So let's start with kind of the dawn of data science. Okay, and there's a lot of mathematics that happened before, but I'm thinking here by the early 2000s. Okay, so the early 2000s is kind of a critical point when things like Google were starting to become widespread used and like actually effective. One of their mottos at the time, well, there's one motto was "Don't be evil," which they've dropped, and then there's another one was to organize the world's information, right? So they were really trying to build a search engine, the idea of organizing the world's information, have access to it and download it. And this was the mantra of kind of a lot of early companies in Silicon Valley. They realized that a lot of what their worth as a company was the data they had collected. Okay, the data on the customers that they had collected. And the reason the data was useful to them was because they could serve personalized ads to you. And this is still most of the economics of Google and Facebook, two of the most valuable companies, right, in the world right now. They're basically there to serve ads to you, okay? And they were able to do this better than linear TV. Back then, it was not because people weren't watching kind of linear TV, except for sports, which is now. There was still more watching TV, but they could personalize the ads. And they needed the data about you to do that. And so in the early 2000s, kind of the big companies didn't really know the best way to do this, okay? So there were these big so companies, they would collect lots of data about users, right? So so this was mostly to serve ads, and this was basically through the web, kind of the web, like Web 2.0, I guess, was pretty new back then. It was pretty cool. And so they collect this data, and they wanted to know how to kind of make inference about this. And so they were hiring lots of people, a lot fewer than have been hired by them now. But one way they said, well, we don't really know the best way to do it. So their idea was kind of release sample data so online, and we will let so academia figure it out. So they released these data sets, and there was all sorts of their most kind of important data. They really wanted to know the best. They would release in these files online. And it was being in a university trying to do research at the time. It was very exciting. We didn't have access to it unless we went to work there or to do an internship there, and it was kind of restricted. But they said, let's release data, and then we'll make these challenges for people in academia and farm it out to all the professors and grad students out there. And so this was great. It still happens to some extent, but basically in the late 2000s, this so stopped. Okay, it didn't entirely stop. There's still some release of data, but it's far less common, especially proportional to the amount of data they're collecting and to the amount of access we had to it, right? The data I interned at some of these companies as a grad student, and kind of their most, what they thought of as, aside from the actual customer IDs and credit cards, what they thought was kind of their most important data to understand is what they spent the time organizing and curating and putting examples on. Okay, it was much harder to do the scraping and downloading and organizing and hosting the data back then. They may have done even more of it if it was as easy to do that sort of sharing the data as it is now. So this kind of, and so this didn't just happen in the big companies, it was happening inside the government as well. And so again, this kind of stopped. So let's kind of like give an extended story about this. So there was so in around year 2000, so Massachusetts decided to release all of the state's employees' medical records in an effort for researchers to study them. Okay, I believe this was from lobbying because there are a bunch of universities in Massachusetts. And I think they lobbied, said this would be a great way for us to do big data science on all the medical records and their government employees. So you should be able to do something like this. They convinced the governor to do this. Said, well, we don't want to kind of give out all the individual information. So we'll be careful about it. We'll wipe out the IDs, but we want to understand where they live, how that affects what is so how this affects their health, right? If they live near the coast or near a factory, is this going to change? Or like near power lines, or like the cell towers were new, does living under a cell tower affect something, right? So they released something with the zip codes, the birthday, the gender of the individuals, but a lot of the health records of them. But this was declared anonymized and safe. Okay. Also around 2000, I think this is still true in most states today with some variation of this. So it was possible to buy the voter records of people for like $20. Okay, you could go to like some government office and you could say, I want the voter rolls of who voted in this election. It doesn't tell you who they voted for, but they want to see who voted. This is important for kind of keeping fair and honest what's happened in elections. You want to be able to check if your vote was counted. You can go down to the office and see if your count is voting. And this information included the names of individuals and also where they were, to say which precinct they were voting in, and also include information about their gender. So okay, and so so what happened is a then grad student at the University of Massachusetts, Latanya Sweeney, said, aha, what if I got both of these pieces of data and was able to combine them together, and she felt high enough confidence, identify the records, the health records of the governor of Massachusetts. And so the story is she actually mailed, this part, I don't know if it's true, she mailed the health records to the governor, said, aha, these are your health records. I was able to de-anonymize, right? So this was not expected. Okay, and so this was kind of a shock. And so Dr. Sweeney, last I checked, now teaches at Harvard, right? This was kind of a big turning point in the field of like privacy in the era of data science. And so the insight here is that you can release one data set, right? So the state employees' medical records, right? And you think that these are anonymized because you wiped all the IDs, but you wanted this other information, right? And so what can happen is you can link, the information about the zip codes, birthday, and gender with the names, zip code, and gender of all the voters. You may not have the birthday, but you can look up someone's birthday someplace else. The governor may post what their birthday is on their voter information, or you can figure this out. And so you can take two different data sets and link them together to make inferences about information supposedly that was anonymized in the first one by linking it with information from the other. So this kind of is a challenge when trying to do privacy in data, in these releases of data. So this was early 2000s, but people were not kind of said, well, this can happen. It's still important to release data. We still want to do studies. So we just need a better kind of understanding of how to release data so it's going to be anonymized. Okay, so how to how can we release data anonymously? So what does this mean? So the goal is to kind of so two things: to somehow keep the anonymity of individuals, and to be able to make an inference. All right, we'd still like to be able to do the sort of data science, data mining, machine learning that we are doing, that we would if we had the full data, but we'd not like to keep anonymity of individuals. We'd not like to be able to identify individual records. We'd not like to be able to identify the record of the governor and send them their medical records. Say, these are your medical records. All right, so how can we keep the anonymity without being able to make an inference, right? And so there were a number of proposals, and so the right way how to do this. Okay, the first one that really tried to formalize this was called K-anonymity. Anonymity. Okay, and so what this says is, before I release, I need to remove information. So the idea is I want to remove information from the records until each combination of the attributes maps to at least K individuals. Okay, so if you've taken a database course, right, you want to think of having each person's unique ID as the key, and there's a table of information, and you want to keep removing information or aggregating something. Instead of the zip code, maybe aggregating it to a set of zip codes, or if their age, round their age into a group of a number of years, or just remove information entirely until for each individual in the records, there's at least K other individuals that have the same actual data which is released. Right? So, okay, so if I have some records, keep removing it, then I don't know which record is mine. It could be up to K other people. So if I don't have my exact address, but instead I have a region on the map that I might live, but there are at least K of my other neighbors, let's say 10 or 20 my other neighbors that have all the same information as mine in the database, then I don't know which medical records are actually mine. All right, there might be some private records which have some information, but I can't know. But like there, but that has also been kind of rounded. Maybe it's something about my health information. I have high blood pressure, or I have some cancer. But there's another group of individuals who also have those high blood pressure and cancer, and I've rounded their geographic information to a wide enough area, I can't tell whose is whose. All right, and so kind of this discussion, kind of what we often talk about, dividing data into the public attributes and the private attributes. So the public attributes can things be like my zip code, maybe something about my age. You can probably find this in the public record. Because I'm a state employee, there's actually a bunch of information about my pay and stuff like that. You can find online. Information about someone's gender may or may not be private, but at least they have some stated gender on their driver's license, for instance. So this information is typically assumed to be things like these are public attributes. If someone finds this out about me, maybe I don't want people to know my age, but okay, it's probably fine, right? It's not a big deal. For me, it could be for like a sports star, right? There were certain like professional athletes who came up from a country where birth certificates were not records are not as well kept, and they may pose to be younger than they actually were because then they have more years in front of them in their career. So maybe age is protected too. Okay, so these things might be private, but for most people, these things, if they're in the open, this is probably okay. And there are also some private records, right? So if someone was diagnosed with cancer, or if they were prescribed a drug that's almost always prescribed to treat cancer, that's basically the same as kind of indicating they would have been diagnosed with cancer, or it's like has diabetes. These information you may just not want people to know, and in particular, depending on what happens with like health insurance, you may not want the insurance company to know this information, because then they may charge you much more for your insurance, right? It could also be your so your search history. So what things have you search for? So Google claims to be very protective about this. They say they do train on search history, but they don't like link it to other parts of your things. And so there's probably some linking going on, but there are certain things they try not to reveal. I don't know if you trust them. So I remember another talk in the early 2000s. One of the kind of former students of my same PhD advisor was an early employee at Google and was the one who put like the spell check into like the search bar. And I remember he came back and gave a talk, and he said that something like the top 10 searches at the time, early 2000s, were variations on the spelling of Britney Spears, right? So they were all searching for the same thing, but it was so popular to search for her. But maybe you would have been embarrassed if that's what your search history was filled with back then, right? So you could think of things that might be in your search history that you don't want everyone to know about. So they're kind of, it might be useful to think about what you want to keep anonymous from these public attributes. They're probably out there, and I need to be cautious about sharing these. And these private attributes, I need to be careful about releasing this. So when I talked about K-anonymity, it did not necessarily talk about the difference between the public and the private attributes, right? So one of the reasons this is not necessarily the most common way to do privacy preservation now is if I'm releasing a bunch of public of like the public attributes, but I can't zero in on up to K individuals, up to 10 people have basically the same sort of public attributes. And so then, but I want to release information about the cancer and the diabetes because I want to study what could be causing the effects of this, right? Does living near some power plant increase the chance of having cancer? So I want to release the information. But what could go wrong is I could release a set of information. I could release a set, and so so this is like the ID. I've got, these are so someone's name, Joe, Kim, Sam, B, a bunch of people, and so I have some information here that has been released, and so the C's are people who have cancer, the no's people who don't have cancer, and so if I've released enough information so I know that these three people are all in the same group. So the information, the public information I've released has so anonymized them. There are 3 K people who all have the same rough information. And so, but maybe what this means is that there are some people on the map, right? And there's a region on the map that they all live in, like Joe, Kim, and B all live in this part of the map. I don't know where they live in the map. And I know that all of them are aged between 40 and 50. And so I can figure out maybe they all voted Republican in the last voting cycle. Okay, or no, I don't have that sort of voting information, but like they all have the same, so gender, for instance, okay? But I have a bunch of public information. I don't know who is who, okay, in here, but they were these 3 lines. So if I wanted to know if someone like Joe was like the governor, okay, what would I know about the governor now? I don't know which record is his, but all 3 of these people had cancer, right? So I narrowed it down so there are only K people. I don't know exactly whose is whose, but they all have cancer. So I've still released information that anyone who fits this characteristic has cancer if I've kind of released the data in this way. Okay? So this K-anonymity, if you're not careful about it, if it contains that private attribute that you want to study, well, I don't know exactly all the properties about them, but I did narrow down that if the governor fits this category, they're one of these K people, and all these K people have cancer. All right, so I need to be a little bit more careful about this. And so this led to some variations on K-anonymity. Okay, the first one was called L-diversity. Okay, so this was K-anonymity. So every person must be at least in as K other people in the same kind of records. But I also have the property that each group, right, of at most K people has some notion of diversity in the private values. Okay, so this means now how we define L diversity is not so important, but let's say if it was cancer versus no cancer, then this would have to be balanced, right? Maybe at least L out of K people have cancer and L out of K people don't have cancer in the group. So then if I identify this group, well, I have to mix into this some people who don't have cancer, right? So now I can go and I can add, I'm gonna put Sam in this group as well. I'm gonna expand the group in some way. So now Sam is also in here. So now if I identify Joe as being in this group, I don't know whether Joe has cancer or not. This ID part is kind of hidden. I don't know who is who in this group, so I don't know if this person has cancer or not. Okay, so this L diversity said, okay, I've solved the problem. Now I don't know if they have cancer or not. But the challenge is, if we're only releasing one attribute at a time, there's only one study, then this is okay. But what if there are so multiple private attributes? So for instance, what if there are two types of cancer? One is going to be so lung cancer, and one is going to be so skin cancer. So now I can have a table that has the ID, which is private, the public attributes, and then the private. Okay, and so then there's lung cancer, and there's skin cancer. Right, so someone can have neither lung cancer or skin cancer. They can have both. They can have just skin cancer, just just lung cancer. And I'm going to group them so that there's some difference in the private attributes. I can't tell whose records are whose, or whose. What this does not prevent against, though, is that there could be a group that everyone in the group has lung cancer and skin cancer. Or so sorry, I did this wrong. So let's say they have lung cancer or skin cancer. Okay, so there's different people in the group, but they always have one form of cancer. Okay, so they don't all have the same form of cancer, but they all have some form of cancer. The notion of L diversity does not protect against this information. I could still identify the governor as being in a group, and I don't know whether they have lung cancer or skin cancer, but I say you definitely have one of those two types of cancer. All right. Or there could be other things where the distribution is generally unhealthy. Now, there's different sorts of unhealthy in the private characteristics, but they're all different sorts of unhealthy. And so there's some health ailment with the governor that you could say the governor is in this unhealthy sort of category. Even though I've anonymized, I don't know exactly what it is. There's something that's wrong with the governor. All right, so this is something we also, so this kind of issue was not solved by like L diversity. Okay, so then there's one other popular measure called t-closeness. Okay, so this is now, it starts with L diversity. This has L diversity. Okay, so which has as part of it K-anonymity, starts with L diversity, but then it says that the private so distribution of values must be close to the full data set. Okay, so now I need to measure some sort of distributional notion of look at the distribution in the set versus the full distribution. Okay, so it has to, every private group must have, some fraction of people who have skin cancer and some fraction of people who don't. Some fraction of people who have neither skin cancer or lung cancer and some fraction of people who don't. And that should kind of match the general or the population. Okay, this should be safe to release. Now maybe I can say, okay, there's I can't, by telling you're in this group, I cannot tell that you're in a sick distribution because your distribution looks like the full data set distribution. All right, so yeah, great. So I have taken the full data set and I've chopped it up into pieces. So all the attributes, so every unique set of attributes in my full database of like all the people who live in the state of Utah, every attributes looks like at least K minus other ones. They have the same attributes. Okay, so that those information could be the location of like where they live, and I've rounded that, their age group that they're in, and I look at different reported genders, right? So I know how many people live in a certain part of the map, right? And I know within that what fraction of them are a certain age group and what fraction are a certain gender. And I can release records of all the people in here and say they all have this. There's at least K people that match this description that I've released. Okay, so I don't know whose is whose. Is all similar to each other. I've rounded it. I don't give your exact address or your exact birth date because that would be able to identify you. But I've rounded this information into groups so that I don't know exactly who's who in the group. Okay, and sometimes you do this separately. You say the public data, I'm going to round to these groups, and then I want to make sure that the private attributes, those can be different within the groups. And that distribution should maybe match, should either have some diversity in it or should match the general population. Okay, so there are probably some of you who have working with data sets where you might realize there's a lot of sort of commonality to some of the data points. If it relates to health information, probably, or some private information, it's probably been rounded in some way. And so this is usually an attempt at one of these privacy measures. Don't shut down. So there's usually an attempt at one of these privacy sort of measures. A lot of health studies use this form of privacy. They will try and aggregate groups before they release it, so that they've kind of rounded the characteristics of people. They will still know roughly they might still know the total number of people who have cancer or diabetes in the group versus what fraction don't. But the attributes they're trying to draw inference from have been rounded in these ways. What's the problem with this sort of analysis, t-closeness and L diversity? Why would this be hard to do data analysis with? It does what? It doesn't necessarily change the distribution. It has to grow the distributions in a way so that if I have two subgroups, that one has more cancer than average, one has less cancer than average, before I release them, I may need to merge these together so they have roughly the right percentage of cancer as average. So that way I don't know if people, I can map them to one of the subgroups. I can't know, do they have elevated cancer or risk or not? At least not too much. Okay. The problem with this is now all of the subgroups, all the groups of data I have different regions of the map, different distributions of age or gender or medical, other public medical history. They all have roughly the same rates of cancer in them. So how can I draw any inference from this? So it becomes harder to draw inference from here. Yeah. So how do I find significant inference or make judgments if all the groups have roughly the same rates? Right. So it becomes, you can still do it and you can still say something. If you aggregate them, it becomes more and more unlikely that an aggregate group will all have slightly elevated rates, but each individually group is not too far away that you can't really draw any conclusions from it. But it becomes much harder to do this, right? So this t-closeness is not super common. Usually they do something like L diversity or K-anonymity. And it's I don't know. I'm usually not, when I've seen like a medical board say this data is okay to release, I'm usually kind of skeptical of whether it's actually been made private or not. Okay, but these sort of notions are quite commonly used in medical data. And in some versions of this, in some of the kind of the online data from the internet as well. All right, let me tell you another important story from the mid 2000s now. So who's heard of the Netflix prize as kind of a data science sort of thing? Okay, so this is the story of this in around 2006. So Netflix, this was still when there was not streaming. They were very forward-looking in the name that it was over the net, but that meant you could log onto a website and order like a DVD. They would send it to you in the mail. When you watched it, you would have to put it in a machine to spin the DVD up. You may or may not know what I'm talking about. And then it would show on your TV. It was very cool. When you're done, you had to send it back in the mail, and then they would send you a new DVD. Okay, now everything's online, but the same principle works the same. But you would put it in this little envelope, and you could write on the envelope if you like the movie or not, right? And so they had ratings of these movies, and it had something like everyone. They had a user ID for Netflix, your login, what your account was. They had what the movie was you had watched, and the date that you were watching it, and then the grade you gave it, like how many points out of 5 you gave it. Okay, and the huge data set. I mean, back then, Netflix 2006, already a very big business. So it was when Blockbuster was going out of business, but had maybe not been out of business yet. But it was still like a very big company, a huge data set. They had another data set that had the user ID, the movie, and the date of the grade they gave the movie, but not the grade. And they wanted researchers to predict the grade on this data set D2. Okay, and they had another, and they held privately. These were both released. Okay, so they made these public, and they had another similar private data set D3 that they could use to evaluate, right? So at the end, they wanted researchers to come up with an algorithm, a machine learning model that predicted data sets on the data set D2, right? And you could send in your model, and once a day they would run your model and report back the score, how well it actually worked. And then at the end of a time period, they had data set D3 where they would evaluate everything. Okay, and so they released this and said, if certain improvement in Netflix's algorithm, the winner will, so it's going to win $1 million, right? So it was 20 years ago, $1 million was, so it was a lot, but this was more important, more than the actual money. this was actually super important point for data science in general. We figured out how to run a bunch of different models and build ensembles out of them from this experiment. This was one of the big takeaways. Another one was these collaborative filtering algorithms came out of this. So this was like hugely important for the development of the field of data science, a great example of cross-validation. And this really caught people's attention. There was like a leaderboard, and a lot of people, I was in grad school, people were watching this leaderboard. There were different groups competing. They were trying to get to like this 10% improvement, and we didn't know if they would make it there by the actual deadline. They were creeping closer and closer. What happened is the groups decided they would be better if they merged together if they had better to merge together at the end, so they would each have one thing they could submit every day. And then at the end, they would combine together their algorithms and run like a joint algorithm and submit this. And they just barely crossed this deadline on like the last day. And there was a competition between 2 or 3 very kind of top groups in the space. So it was very exciting. So this, like I said, this led to lots of cool research, important development. It turned out, though, that the raters of these movies who had Netflix, especially back then, these were people who really like to watch movies. They also often rated movies so also on IMDb, right? So this is, the website IMDb, and there are ratings on there. And there's lots of people rate movies on there, apparently. I've never done this or looked at the ratings, but there are a lot of people who do it. There it has a user ID, and you can often identify who it is. They might have their real name and has the timestamp and their rating of the movie on there. But as you can guess, it has the timestamp and something similar to the grade of the movie from Netflix. And the people who watched them, they usually wrote these reviews the same time they got the movie from Netflix. So the timestamps lined up pretty well, and the grades probably lined up pretty well with the ratings. But this one had the user ID in there. But if someone was watching some like naughty movie on Netflix, they didn't want to rate on IMDb, they might not post that on IMDb, but Netflix had all their information. Okay, so there were some researchers who were able to kind of link these data sets together. And by finding people who rate similar movies and similar scores at similar times, and something like they felt like they could confidently identify like 90% of people in so the Netflix data set who had accounts at IMDb, right? And so this was okay. This made people uncomfortable. There was so embarrassing movies. So there was a class action lawsuit filed against Netflix because of this. It was dropped at some point. I don't know whether there was a settlement or something, but this was dropped. But unfortunately, because there was a very publicly planned sequel for the Netflix prize that the community was very excited about in 2010. But before then it was delayed, and eventually they decided not to do it. They decided that the privacy concerns were too big that they could probably link the data. And so, this was kind of the end of really kind of companies being not careful about releasing these cool big data sets that involve their customers. And I mean, this really helped Netflix. Their rating system got apparently much better, and recommendations got better at this time. We learned a lot, but the privacy concerns stopped them from being able to release data sets of this form. Even with K-anonymity and stuff like that, they figured, by linking these things with other data sets, this attack was always going to be present in some way. Okay, so this was kind of not the end of the story. We were kind of unsatisfied with the K-anonymity type of anonymization. It either didn't really provide anonymization or it degraded the data too much. And so places like Netflix were unsure about what to do. And so this is around the development of this new idea called differential privacy. Okay, so this is a type of privacy guarantee you can put in data, and then there are different algorithms to induce this privacy into the data. So it's like K-anonymity is kind of a way, a claim you can make about how much privacy you have in some data that you've released. Okay, so it's a guarantee on the a release of some data x1. So what's called, the reason it's called differential privacy is so that you could compare it to. So if there's another data set, x2, and we have something like the difference between x1 and x2, or often we write this as x1, the symmetric difference between x2 is equal to 1. So that basically, think of the data set is off by like one value, or what is in the data set is off by the content. There's one data point that's missing, but that's different between x1 and x2. Okay, so if we somehow, there are two nearby data sets that are very similar to each other, and their difference is 1, okay, and well, 1 can mean various things, and you get to decide what that means. Then I want to say something like the probability, if I make a query, is true, or is some is equal to some value, divide by the probability a query, this should be x1. If I do it on D2, which is a neighboring data set, is also V. If I look at the ratio of these probabilities, okay, then this is at most e to the power epsilon. Okay, and e to the power epsilon, this is equal to e to the power epsilon. This is roughly equal to 1 plus epsilon. So think of epsilon as an error tolerance, like so it's like 10%. So the difference is off by the ratio off is like 10%. So the probability of the two events should be close to each other. So the idea is I have released some data set x1, and I've released it in some way with some randomness. Okay, I've added some random noise in some way into data set x1, and then I make a query and I get a value v. Okay, so I query something, I ask a question, how many people had cancer? What's the probability this person has cancer? It gives me a value. Let's consider a neighboring data set that does not have my data in it, right? So the difference is off by 1, and I've released this. I can make a query on a differentially private query on the data set x2, and I also get, there's also a chance that it reports the same thing. What's the ratio of those probabilities? Those probabilities are always close, then I say this is differentially private. This would imply epsilon epsilon differential privacy. So often we'll abbreviate it DP. Okay, so if I have this for two data sets, any two data sets that differ by 1 in some way, right? My data point is in there or not, and I make a query. I'm allowed to make a query that somehow adds noise to the result. So the return of a value is probabilistic in some way. And if the ratios of the probability are always bounded by 1 plus epsilon, they're within 10% of each other, then I can say this is like epsilon differentially private. I don't know if my data is included there or not, or it's hard to tell. There's some, I might be, okay, I think it's probably included as opposed to probably not included, but I'm not that sure. You know, the probability is roughly the same, it's included or not. Okay, so the goal is to release the data sets so that I don't know if the true value up to 1, or I don't know if my data point is in there or not. I have some, no matter what query I ask from a family of queries, I don't have very high confidence that includes my data. So, and I want this to hold, I want to hold for a class of these queries Q. So Q is in this. So I can ask a bunch of different types of questions, and for every question I ask, I have this property. Okay, and so this is the general way. So this is, I think, a little bit kind of tricky to try and understand. So let me try and go through some examples. Okay. So let me say, if I say that the probability of Q of x1 equals some value r versus the probability Q of x2 equals this value r, like what's the probability that people in this set have cancer? And let's say that this is equal to 2. All right, so this means that I'm twice as likely to predict that x1 is the true data than x2. Okay, so if I get a differentially private, if it's 1, so this is, think of this as 1 plus epsilon. That means that epsilon equals to 1. So this would be 1, so 1 dp. Then I'm twice as likely to predict data at x1 or x2. This is still kind of okay, right? Okay, maybe it's 2/3 of the time I predict x1 and 1/3 of the time I predict x2, but I'm not that sure about it. All right. Well, if instead I have that the probability of query x1 equals some value over the query x2 equals a value, if this is equal to like it's like a value 99, right? That means that I'm like 1 out of 100, I think it's x2. 99 out of 100, it equals x1. I'm pretty confident it equals x1. Okay, so this ratio is not as good here. Okay, so I'd like this to be small. Anything under 2 is probably acceptable. Okay, so we'll use epsilon. So we're gonna kind of use epsilon, which is going to be a value, that could be anything. Okay, but usually epsilon is less than 1 is probably okay. I don't have that much confidence if this ratio is 2. Okay, and I'd like it to be smaller. I'd like to be, if it's 1.1, then that's something like 55% to 45%. Might be, give me something like epsilon equals 0.1. Okay, but that'll be more expensive to do. So let's say that the value, this data is actually like just a real value. Okay, so for instance, an example the height of um uh uh um like 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 the height of Sylvester Stallone, right? So his height is a carefully guarded secret in Hollywood. There are websites devoted to it. So it's, but let's say his height in inches. What did I say in my notes? I think it's probably um so so 5'8", right? So how many inches was that? Okay. Now I've lost this in my notes. What, uh like 70 inches? Okay, I used in my notes 68 inches. Okay, so let's say it's 68 inches. And so I wanted to know if he wanted to say that his data set, so let's say X1 is 68 inches and X2, he says, I want to think it might be 69 inches at least, right? So he's always in lifts and shoes, or he gets the photo and the camera angle just right. So he wants it to be 69 inches. So now the difference between X1 and X2 is going to be 1. Okay, so I want to be able to hide this difference. And one way to do this, to hide this, is the query, the query of the height of X1 is going to give me X, the true value, plus uh, uh, um, plus some Laplacian noise. Okay, so I'm going to take this Laplacian value and I'm going to add some noise to it with bandwidth W. So this Laplacian, it's like a Gaussian distribution, but it's pointier. Okay, so it is the exponent, it's 1 over 2W exponent of kind of the value X divided by so by W here. And so I'm going to add this with Laplacian noise with this bandwidth factor. This bandwidth factor equals to 1 over epsilon. Okay, so if I want to have more privacy, I need to add more spread out noise to it, right? So if I make the noise more spread out, I'm adding to it, I'm going to have more full privacy. Okay, so now let's say, what's the probability? Let's say he said the true value after some way he's manipulated the camera or shoes and so forth is that I'm going to query this and get some value S. And let's say the probability that the S is required is like the reported value is, the observed value is 70. Okay, versus the probability that S prime is so 70. Let's say this is S1 and S2. Let's do that. So now the 70 came from either 68 plus Laplacian noise or 16 or 69 inches plus Laplacian noise. It was reported the value was 70. Let's look at the ratio over these two. This is 1 over 2W X of 68 minus 70 divided by W divided 1 over 2W X 69 minus 70 divided by W. Okay. What's going to happen now is these two things will cancel out. Okay, and I can look at the ratio of the exponents, and the ratio of the exponents is going to equal to exponent of 1 over W times 68 minus 70 minus 69 minus 70. Okay, when I take the ratio of two exponents, I can actually take a single exponent and subtract their contents. The 1 over w factors out in front. This 1 over w, and the difference inside of these is 68 minus 70 is 2, 69 minus 70 is 1. Okay, so the difference in these values is 2, 1 over w2 minus 1 over w1. So I'm going to get just equal to exponent of 1 over w, because the databases or the content of the value is off by 1 here. So it always simplifies the exponent of 1 over w. So if I set w equals to 1 over epsilon, then this equals exp epsilon, right? Because I set, w equals to 1 over epsilon, then I get that the ratio of these is always exponent of 1 over epsilon, which is roughly 1 plus epsilon, right? So if I add Laplacian noise with the bandwidth of 1 over epsilon, I get epsilon differential privacy on these individual values. The probability, the ratio of the probabilities of values I'm trying to observe, which are off by 1, 68 or 69, if I observe something that's 70, then I don't know whether it's 68 or 69. I can look at the ratio of which one is more likely. The ratio of which one is more likely is always exactly the exponent of epsilon, right? So if I can draw a picture here, so I have 68, and this is 69, and for 68, I draw this Laplacian distribution. I can also draw a Laplacian distribution at 69, and always the ratio of these inside this range is even closer, but these ratios of the probabilities are always going to be the same. I didn't draw them quite right. They go exponentially down to 0, but the ratio of them, one divided by the other, is always going to be, the ratio is always x of epsilon equals approximately 1 plus epsilon. So if I add Laplacian noise to it, every time I'm asked a question, I get this epsilon differential privacy on this value. Okay? It's kind of make a little bit more sense now. I release the data with noise, and if I do Laplacian noise, then I get this sort of guarantee. You can say something a little bit weaker if you add normal noise instead of Laplacian noise, but Laplacian has this nice property that they decay at the equal rate. Okay, and so the ratio of the probabilities is always exactly x of epsilon, which is approximately 1 plus epsilon. Okay. Let's do another example here. Another famous example is the binary example. Okay, so now I have x1 equals 1 and x2 equals 0. Okay, so I ask the question, is something true or not true? And I'm going to give a value between 1 and 0, right? So now my query on x1 is going to give me the value of x1 plus Laplacian noise 1 over epsilon. Okay, and I want to know now the probability that I return query of x1 equals to, I observe some value. The value I observe is like, let's say it's 1.2, right? This is whatever value I've given. And I have this other, right? So I can go through the same exercise and write down that this is going to be x of 1 minus 1 divided by 1 over epsilon, x of 1 or 1.2, 1.2 minus 0, 1 over epsilon, right? And so this will simplify to x of epsilon times 1.2 minus 1 plus 1.2 minus 0, right? Because this is the subtraction of these two things, right? So it's always 1.1 minus 1.2 minus 1, 1.2 minus 0. Okay, so it's always these off by 1 here, right? And this will exactly be. So if I have a binary object, is it there or is it not there? I add Laplacian noise. I no longer get a binary value, I get a real value, but the ratio of these is always going to be bounded by exponential of epsilon. Okay, so so what happens is instead of a single object in a set, what I often get is a so a database where x1 is going to be a sequence of 0, 1, 0, 0. Okay, so I'm going to think of this as a database, and this is 1, 0, 0, 0, 0, and this one is different, and I'll think of this as being my data is here, and this is a database of a whole bunch of people, and this is if they have cancer or they don't have cancer. Okay, so I have a bunch of people who have cancer or don't have cancer, and then I can ask a query on the database, and I can ask them, okay, how many people have cancer in this set? Well, I'm going to release this with some noise, with Laplacian noise onto this, and I won't know whether my data, did I have cancer or not, was returned in this query or not, right? So now the query is on x1 so it's going to be a range was the intersection of x1, where this is a range query that says all the people who satisfy this property. I want to ask a query, and I'm going to add some Laplacian noise onto this. Okay, and I think that this range query, I can ask now a subset of people. I can count how many people have cancer, and then I can add some Laplacian noise on this, and I can release this information. Okay, so first I want to say the US census in 2020 was released with differential privacy. So what they do is they broke people down into sub-blocks of the population, these census blocks. They want to release how many people are in each census blocks and how many people are of a certain age and certain specific information. And all that data was released with this Laplacian noise onto it. Okay, it was controversial that they did this. The US law is kind of contradictory, that every 10 years they need to create a census and count how many people live in certain areas and districts and report certain information about them. And it's useful for all sorts of policy setting. But they also say you can't release individual information about people. And what was happening is that through these privacy attacks, you could recover individual information about people. They'd realize, oh, only one person in this area has had these characteristics. It must be this person. So they added differential privacy. The problem is that the Laplacian noise made some of the values, like how many people in here are over 65 years old, it would return answers that were sometimes negative. Okay, if you don't allow it to be perfectly Laplacian noise, right, some of it is less than 0, then it doesn't actually work. You can't guarantee it's the same. Otherwise, it renormalizes the rest of it, and everything is kind of off. So they released it, and it was very a lot of controversy because there were, it released some values which had to be positive, and so, but they were released as as values which are negative. They were unbiased estimates. So you could say, well, I know they must be at least 0, so I can round them up. And it was a mess. There's a lot of controversy about this. There's another issue here, which I'm not going to get a chance to talk about. It's described in the notes. If I can ask more complicated queries like this, I can chain them together, right? So I have data like this. I can ask a range query that looks like this range query, and then another range query that looks like this. And I can subtract these two values. And if this is my data, I'm getting the true value plus noise. And I can subtract the red value from the green one. And I can take the average. And I can get, that gives me an estimate of this value. Okay, I can also ask another range query that just asks this value. And they'll independently add noise to it. Well, now I get a better estimate because it's unbiased noise. I can take more combinations of queries to get independent estimates of my true value, and I have more knowledge than I actually said by just this error, because each time I add independent noise, and I can take the average of all these estimates to recover some information. So when I release a database of information that can ask queries about, I have to be more careful about how I do this. And there are clever ways about where you inject the errors. You build a binary tree and you inject error at every kind of node of the tree. And then when you answer a larger query, you aggregate, you only use the values on the nodes, internal nodes, and you get like some logarithmic of factors. So I have to add logarithmically more noise, and everything still magically works. Okay, and we're not going to get into this, but when you have more complicated data where the queries can overlap and you can slice and dice things, you have to be even more careful about this. But people have built a whole bunch of infrastructure around differential privacy. You can run like gradient descent in a way that every time you calculate the gradient, you add differential privacy, and you can guarantee to learn something while preserving the data in some way, right? So there's a lot of infrastructure built around this idea. It's controversial. Not everyone trusts it. Sometimes it seems to add too much noise into it. Sometimes it's too slow to use. Okay, but this is kind of the state-of-the-art tool for how to ensure privacy. We don't have anything that's better than this. All right, okay, I've run out of time. We'll stop here. All right, and see you all on Wednesday.